Good evening, guys. Am I audible? Those are online. Am I
Yes,
audible?
sir. Yes.
Yes,
Oh,
sir.
okay. We'll get started. Just a minute.
Sir,
Yeah.
so tomorrow's test is only offline, sir.
Yeah.
Okay.
Right. So those are online. Are you able to see the screen? Right? Are you able to see the screen?
Yes, sir.
Okay, listen. So what were the previous topics that we discussed? So what were the previous topics we discussed in mechanical properties of fluids? It's tighter. Maybe you can change the share. Okay. What were the topics we saw? Can you tell me? Don't remember. We discussed pressure. Then then we saw Pascal's law. Then we saw barometer. Then we saw something called as a manometer, right, which is used to measure the pressure of the gas in a vessel, right? Then so we saw the effect of gravity. Then we got an expression, right? Pressure is equal to rho gh, right? So I hope these are all the points that you're clear with, right? Now, listen. Now we'll go to the next part of this chapter, which is viscosity. Okay. So we'll go to this concept of viscosity. Here, when you speak about viscosity, right, this comes into picture when a liquid is in motion. So in the previous concept, right, in the previous topics that we discussed, if you see all the concepts were related to the fluids at rest. Now here we are going to discuss about the fluids in motion, right? So before we see this, observe. So there is a small activity. Let me see how this can be played. Let's see. See, what I've done is we have taken two liquids, right? One is basically water kind of thing, and the second is honey. Okay. Now, see, what we did is I took a cardboard, just dropped in some honey, and you're able to see it is flowing, right? Now, I'll pour another liquid, see how that is going to flow. It's some oil, actually. Okay. You're able to see the difference. So, what is happening here? It's not about density.
The honey is resistant to flow.
So, this is an experiment or an activity to understand the concept of viscosity. Right? Why I showed this is based on this, I'll be relating it to the theoretical concept. Now, you're able to observe that the liquid is flowing, right? One is moving slow and the other is moving a little fast, right? So, which one do you think will be able to move more fast? Can I think like this? The one which is experiencing lesser friction. Like friction is not the right word. I'll come to that. So the one which is experiencing lesser resistive force is the one which will be able to go with a faster rate, right? That's what happened with this. Now, if I look at this from the other angle, see. 1 minute. So when I'm going to look at it this close, right, you're able to observe something. See, this particular angle is very important for me. You're able to see this, right? So here what we are going to do is we are going to understand this concept in terms of layers. Okay. We'll see how this can be broken into layers and how each layer is offering the resistance to the subsequent one. Okay. Now, if you look at it, so this is the side view of the liquid where you had that cardboard, right? That cardboard is the fixed surface. And the liquid had some amount of layer associated, some amount of thickness that you saw from the side, right? So in the thickness, what is happening is, can I break it into multiple layers? So with respect to the cardboard, from the cardboard till, let's say it is having this level of thickness, from this fixed surface to this thickness, can I break it into multiple layers? Something like this. So when you break it into layers, you can observe one thing that is happening, that is the layer which is close to the surface or moving on the fixed surface. The layer which is moving on the fixed surface is going to be almost at rest. It is going to be at rest. Whereas from the fixed surface, as you move away, right, you can see that the speed of the liquid is going to increase. So that gives us a hint stating that there is some amount of resistive force existing between the set of layers from the fixed surface to the top. Right. So are you able to see this? Now, if you take this layer concept, right? So the fixed surface is obviously going to have what speed? So the fixed surface is obviously going to have speed of 0. Okay. So it is going to have speed 0. Now, as you move away, right, when you go from this layer to this layer, you can see that the speed has got increased to a non-zero value. After that, it will be increasing even more, then even more like this, the speed is going to increase. That is why the size of the vector is more. So the topmost layer is the one which is going to have the maximum speed. That is what we call it as the surface layer. So that is going to have the maximum speed. But what is going to happen between the layers itself? Let me take two random layers, A and B. If you observe, between two layers, there is going to be a resistive force that will exist. And what is the name of that resistive force? This is what is called as viscous force. And the phenomenon is called as viscosity. So the force is called as viscous force, and this phenomenon is called as viscosity. Am I clear with that? Right. Now, if you observe, so what is viscosity? When I say phenomenon here, it is also the property of the liquid, right? It is a property of the fluid by virtue of which there is an internal force of friction which comes into play between what? Between the, where is the friction coming? It is between the layers. So friction, a force of friction comes into play when a fluid is in motion and which opposes the relative motion between its different layers. Am I clear with that point? Right. Now that is the property that we have discussed now. See, the next question is, the backward dragging force is what is called as the viscous drag, or you call it as viscous force. Now, how is this going to act with respect to the surface? Backward is okay. Okay, here, okay, I'm able to understand that the arrow marks are flat. Then I can say that the the viscous force is in the opposite direction. But you need to understand what will happen if the surface is going to have some curved shape. If there is a curved shape, then how is the frictional force going to act? It will always act tangential, right? It will always act tangential on the layers of the fluids in motion. And what does it try to do? It tries to destroy its motion, right? Now, what is the cause of viscosity? So that is what I explained. The cause for viscosity is the speed that is changing between the different layers. That story I already told you, right? So consider a liquid moving slowly and steadily over a fixed horizontal surface. So each layer moves parallel to the fixed surface. So each layer is going to move parallel to the fixed surface. Then what will happen? The layer in contact with the fixed surface is obviously going to be at rest, right? And velocity of every other layer increases uniformly upwards as shown by the length of the arrow marks. Right. Next. So you're able to understand this concept, right? So first make a note of this. Can you just write down the quick points? Right. Don't write the whole thing. Draw the diagram. Done? Done? Did you understand the concept? Right. So if they ask you what is the cause of viscosity, what will you say? So with respect to the fixed surface, if you break the layers of the liquid into multiple parts, then what are you supposed to say? The layer which is moving on the fixed surface is going to have zero velocity, right? And as you go from the fixed surface to the surface layer, what will happen? The speed will increase, right? So having these 2 points in mind, we are going to derive the expression for one of the important parameters called as the coefficient of viscosity, right? So what is the coefficient of viscosity? Let's see. So next topic is going to be coefficient of viscosity. Suppose, let's say the 2 layers are taken in this format, right? If suppose I say that the speed of the layer P is going to be V, then what is going to be the speed of the layer Q? Is it going to be less or more? Obviously, it will be more. So how much is it going to be? It will be V plus dV. Okay. Let me say that the distance of this layer P from X is the distance of layer P from the fixed surface is X, and the distance of layer Q from the fixed surface is X plus dx. Right. Then certain parameters are observed experimentally. What is it? It has something to do with the viscous force. So what do you think are observed? Force is directly proportional to mass. If mass is to be spoken, why are we taking layers like this? Okay, see, basically try to understand. Okay, there are 2 layers, right? There are multiple layers. There are 2 layers for which we have taken the area to be A. The bottom layer is going to move with the speed V, and the layer on top of it is going to move with the speed of V plus dV. Right? That's what the cause of viscosity is telling us. Let's say the bottom layer's distance from the fixed surface is x. Then the distance from the fixed surface to the top surface is going to be x plus dx. Have this in mind. Now the question is, this viscous force is observed to be directly proportional to something. What is it? What is it? So it is this thing. So the force of viscosity, viscous force, which is acting tangential between the layers, is observed to be directly proportional to the area of the layers in contact. So F is directly proportional to A. Secondly, it is directly proportional to a concept called as velocity gradient. I'll explain it. Okay. So F is directly proportional to something called as dV by dx. Now, if you combine these 2 equations and write, right? So let me explain it. Force is observed to be directly proportional to A, and the force is observed to be directly proportional to what gradient? What do you mean by gradient in the first place? So basically, what is the other name for gradient? Gradient has another name. It's called as slope. So gradient is slope. It's also called as slope. So you will be seeing 2 terms in physics. Okay, remember that. One is you will see something called as rate. When you see something as rate, if I say rate of change of velocity, then it is dV by dt. If I use gradient, then you need to give a prefix to it. So for gradient, you will always have prefix. If suppose you give the prefix as velocity, then it is understood that you are trying to differentiate velocity with respect to distance. So gradient is used when something is differentiated with distance. Suppose if I have to define something called as potential gradient, only for understanding I'm telling you. So you see the word gradient, what should come to your mind? Denominator is x. And what should be the numerator? The prefix. The prefix of that gradient should be the numerator, potential. In a similar way, gradient, what comes to your mind? Dx in the denominator. So what is the prefix? Velocity. So what should be in the numerator? So that's why force is directly proportional to something called as velocity gradient. So it defines the rate at which the speed is going to change with respect to distance. Okay. Now, when you combine these 2, what are you going to get? F will be directly proportional to A into dV divided by dx. Right. Now, if I remove the proportionality symbol, I need to introduce a constant. What is it going to be? F is equal to Since this is a resistive force, the force is going to be negative. Okay. So you have a negative force. You have this A into dV divided by dx, right? The constant that we are going to introduce will be of this symbol, which is called as, it's called eta. Okay. So this eta is what is called as the coefficient of viscosity. Now, what is our objective? We don't want the viscous force. We want the coefficient of viscosity. From this, can I rearrange the equation and write eta is equal to F divided by A into dV divided by dx? Are you able to understand? So if you write it like this, it will help us to derive the units and the dimensions of it. Right. So what you do is write the heading as coefficient of viscosity, draw this diagram. After you draw the diagram, write the mathematical equations. Yeah. Shall I proceed? If you see, what did we write? F is equal to, if I remove the minus sign, I can write it as eta into A into dV divided by dx. Now, the question is, I want to give a definition to this coefficient of viscosity. Listen to this carefully. Listen to this carefully. So the coefficient of viscosity, which parameter do you think is supposed to be related? Which is the most important parameter? So for coefficient of viscosity, it is derived from which parameter? It is force. So I will try to define the coefficient of viscosity in terms of force. Look at the way the definitions are formulated. Okay. If I want this eta to be equal to the viscous force, what parameter should I substitute as 1? If I want this eta to be equal to F, what should I substitute? So I should substitute A is equal to 1 unit and dV by dx is equal to 1 unit, right? So if I write A is equal to 1 and dV by dx is equal to 1, then will I get F is equal to eta numerically? Now will you be able to define it? Right, how will you define it? See, listen. Coefficient of viscosity of a liquid is defined as the tangential viscous force. The coefficient of viscosity is the tangential viscous force under what scenario? When you maintain a unit velocity gradient. So dV by dx is 1. When you maintain a unit velocity gradient, right, between its two parallel layers, each of how much area? Each of unit area, because you put A is equal to 1 and dV by dx is equal to 1 to get this value. I hope it is clear. So how will you define it? It is defined as the viscous force, right? It is defined as the viscous force which can be generated when the velocity gradient is unit value and it is acting between two layers whose area is unit value. Are you able to understand? So make a note of it. No, I want you to derive what is the SI unit of eta. So derive and tell me what is going to be the SI unit of eta. That is a dimensional formula. I'm asking the unit. It is numerically, that is why it is mentioned in the bracket. They are not dimensionally the same. So what will you get? Eta is equal to F divided by A into dV by dx. So how much are you going to get? Newton divided by what is area measured in? It is measured in meter square into this one is there, no, meter per second divided by meter. So Newton second meter power minus 2. Right. Similarly, derive the dimensional formula and tell me. So dimensional formula is going to be. So what is the dimensional formula of Newton? It is ml, okay, into T into L power minus 2. So how much are we going to get? You will get ml minus 1 T minus 1. So I hope this is clear to you. Right. Are you all clear with this? Right. So let us see what are all the units of coefficient of viscosity. So we saw what is the SI unit. SI unit is going to be Newton second meter power minus 2, or is it possible for you to define it in terms of kilogram? So how will you write it? In Newton, you can write it as kilogram meter per second square into, you have second into meter power minus 2. So this will get cancelled. Kilogram meter power minus 1 and second power minus 1. So you will get something like this also. Right. So this value Newton second per meter square has another name called as, you have heard this? It's called decapoise. What is this? Poisson. In the language in three, French actually. எனக்கு உங்களுக்கு எப்படி சொல்லி கொடுத்தாங்கன்னு தெரியல. Poisson, whatever you call it, okay. So we'll go with the Indian diction, Poisson. This is actual pronunciation, okay. Poisson. Okay, this is how it is pronounced. Anyways, we'll go with the school versions, Indian school version, Poisson. Okay. So this decapoise is also called as Poisson, right? And let us see what is going to be the Celsius unit of it. So what will be the Celsius unit? In the place of Newton, you will replace it with dyne, and second is second only, and in the place of meter power minus 2, you will replace it with centimeter power minus 2, right? And similarly, what is the other form we have? You have kilogram per meter per second. No, you can write it as gram per centimeter per second, right? And this has another name called as poise. Now here, if you see, this is poise, this is decapoise, right? Deca means how much? 10. So how are you getting it actually? When you write Newton second inverse, Newton second meter power minus 2, if I want to convert this to dyne, what are we supposed to do? So 1 Newton is how many dyne? 10 power 5 dyne, right? And second is going to be second only. What about meter power minus 2? So how much will you write? 10 power minus 4 centimeter or minus 2. So how much is it going to give you? 10 times dyne second centimeter or minus 2. So what is this called as? Poise. So 10 is deca. Combine both, it is decapoise. Clear with this? So that's why we have that name. Right. So what is the relation between these two values? So obviously I've derived it, right? Is equal to 10 poise. This we have derived. Are you all clear? Clear? உஞ்சில ஒரு doubt இருக்கு என்ன? Sure. Okay. So Now the first actually by mistake I wrote it. Right. Shall I proceed? So now you understood what is coefficient of viscosity. Can we just quickly revise what we discussed? So what is it? First, let's come to the concept of viscosity. Right. So what is this viscosity? It is a property of a liquid due to which there is going to be a resistive force existing between the subsequent layers of it. So how is it going to act? The viscous force is always going to act tangential to the layers that are in contact. Okay. Second thing, how is that frictional force related to? What are all the parameters on which it depends on? Suppose you consider two layers of area A each. The bottom layer, let's say it is going to move with the speed v, and the top layer is going to. So the bottom layer is going to move with the speed v, and the top layer is going to move with the speed of v plus dx. So from the fixed surface, what is the height of the bottom surface? X. This will be at x plus dx. So if you're able to calculate the difference in the velocity between these two layers and divide it with the distance between these two layers, you get a parameter that's called as velocity gradient. So what was the viscous force observed to be? Viscous force is directly proportional to the area, and viscous force is also directly proportional to the velocity gradient. So F is directly proportional to A into dv by dx. When you remove the proportionality symbol, you will introduce a constant eta. So negative, actually it is not minus eta. Minus sign indicates that it is a resistive force. So the constant that we introduce is eta, right? So that has to have a fixed value for different liquids. Now the question is, what is going to be the SI unit of eta? It is going to be Newton second meter power minus 2, or it is also kilogram second inverse meter inverse. So what is going to be the CJ's unit of it? 9, okay, gram centimeter inverse second inverse, or it is also going to be 9 second centimeter minus 2. So please be careful when you write it in terms of dyne. The second has no power. The second has power 1. Whereas when you write it in gram, the second has power of minus 1. It might confuse, so please be careful with that. Right. So what is the other name for this dyne second centimeter minus 2? It is called as poise. Similarly, the SI unit is also called as decapoise. Right. So we saw what is the relation between poise and decapoise also we derived it. Right. Now we'll go to the next topic. But before that, we'll try to solve one or two problems based on this. Problems are simple. Okay. So since you know the formula, I would directly ask you to solve this problem. So tell me how to do this. There is a metal plate 5 centimeter cross 5 centimeter. It is resting on a layer of castor oil, right, which is 1 millimeter thick, whose coefficient of viscosity is 1.55 Newton second meter or minus 2. Find the horizontal force required to move the plate with a speed of 2 centimeter per second. So tell me how to do this. So area is 25 into 10 power minus 4 meter square. So what is going to be the value of dx? Instead of dx, can I write it as delta x? So what is delta x here? So it is 10 power minus 3 meter. What is the coefficient of viscosity? It is 1.55 and it is in SI unit only. So Newton second meter minus 2, meter power minus 2. Find the horizontal force required to move the plate with a speed of 2 centimeter per second. So delta V expected is 2 into 10 power minus 1. Am I right? Now, tell me how are we supposed to calculate the force? So F is equal to A. A is 25 into 10 power minus 4 into this eta is there, that is 1.55 into delta V by delta X, that is 2 into 10 power minus 1 divided by delta X is 10 power minus 3. Can you calculate and tell me? So what is 1.55 into 2? Now first we'll do this, no? It's 310. 310 into 25. Or 310 means it is 3.1. So 3.1 into 25 is approximately going to be 75 point something. Or 77, huh? How much is it coming? So it is 77.5 into what is the 10 power minus 4? 10 power minus. So this should be the force that is required to overcome the viscous force to make it move. Let's check the answer once. Yeah. So 77.5 into 10 power minus 2. I hope it's clear. Right? Shall I proceed? The next question is, a square metal plate of 10 centimeter side moves parallel to another plate with a velocity of 10 centimeter per second. Both plates immersed in water. If the viscous force is 209 and viscosity of water is 0.01 poise, what is their distance apart? So same thing, collect the data. A square metal plate of side of 10 centimeter side moves parallel to another plate with a velocity of 10 centimeter per second. Take the data. Area is 10 power 10 into 10 power minus, okay, it is 100 into 10 power minus 4, that is going to give you 10 power minus 2 meter square. Okay, next. 10 into 10 power minus 1. So how much is it going to be? It is 1 meter per second. Is it correct? Sorry, 10 power minus 2 will be 10 power minus 1 meter per second. Right. Both plates are immersed in water. If the viscous force is 200 dyne, so capital F is equal to how much? 200. I think it is better we deal everything in SI unit itself, no, because everything is given in, yeah, SI unit. So we'll take the data in terms of SI unit. Area is how much? 100 centimeter square. What is going to be the velocity? 10 centimeter per second. What is going to be the force? It is 200 dyne. Eta is how much? 0.01 poise, or I can write it as 10 power minus 2 poise. Right. When I take all these values and substitute, one unknown, one equation. So F is equal to eta into A into dV divided by, or delta V divided by delta X. So F is how much? 200. What is the value of eta? 0.01, that is 10 power minus 2, into area is 10 square, into delta V is 10, the whole divided by delta X. Answer is 1 by 2. So this will get cancelled. Yeah. So delta X will be equal to 1 by 20 what? Centimeter. So 0.05 centimeter. I hope it's clear. Clear. So those are online. Are you all clear?
Sir, I couldn't hear you.
But I didn't get you. Did you speak something, Aravinda?
I couldn't hear you, sir. You said something.
You didn't hear me.
You said something before.
Okay. I'm asking, are you all clear with the problem?
Yes, sir. Yes.
Okay. Okay. Right. So everything else is, see, similar kind of a problem, same formula applied, you will get the answer. Okay. So shall we move on to the next concept? It's a little bit of theory again. Okay. So now we'll do a comparative study. Listen. Now we'll do a comparative study between the viscous force and the solid friction. Okay. So the points of similarities are both viscous force and solid friction, they are going to come into existence to oppose what? To oppose the relative motion. They're going to oppose the relative motion. Second, obviously both are going to oppose the motion. And what is going to be the third point? Both are due to the molecular attractions. Right, both are due to the molecular attractions. Okay. Now the next question is, what are the differences between them? What are the differences that are existing between them? Viscous force is directly proportional to the area of the layers in contact, whereas the solid friction is independent of the area of the surface in contact. Okay, that is the first difference. So what is happening here? Viscous force is directly proportional to area. We wrote that no, F is directly proportional to the area which is in contact with, right? Whereas the solid friction, it is independent of the area of the surface in contact. Second, here it is directly proportional to the relative velocity between the two layers. If you are writing that velocity gradient, no. So the viscous force is dependent on the relative velocity that is existing between the two layers, whereas in the case of friction, it is independent of the relative velocity that is existing between the two solid surfaces. Right. And what is the third difference? Here we don't speak anything about normal force. Right. So it is independent of the normal reaction between the liquid layers, whereas in the solid friction, that plays a very important role. You remember we wrote all the equations as mu into n. So it depends on the normal force, right? So it is directly proportional to the normal reaction between the surfaces in contact. So can you quickly summarize what are they? Don't look at it. Just try to recollect. So viscous forces, so you recollect that F is directly proportional to A and directly proportional to dV by dx. Okay, have these two in mind. So viscous force is directly proportional to the area of the surface in contact, whereas the solid friction is independent of area. Second, viscous force is directly proportional to the relative velocity between the layers, whereas solid friction is independent. Viscous force does not depend on the normal reaction offered by the surfaces of contact, whereas solid friction is directly proportional to the normal force applied on it. Sorry, normal force between the surfaces in contact. I hope it is clear. Right. Shall I proceed? You're writing? Okay. Sorry. Have you done copy? Okay, next. See, the next question is variation of viscosity with temperature and pressure. So, is there a possibility where we can change the temperature of the liquid and change its viscosity? Right? Let's see. First point is effect of temperature on viscosity. So, let us see what it has to tell. First, when liquid is heated, what do you think will happen? Let me see what is your understanding. There is a viscous liquid. Let's say there is honey. Okay. If I give you honey and I ask you to heat it, right? So first what we are doing is we are pouring some honey. You can observe that it is going to flow slowly. Now you are pouring honey after heating it. Do you think it is going to flow slowly or faster? So it will flow slow. Compared to the previous case, it should become more viscous, right? You think so? Why? When it is going to expand, what is going to happen? Let's see. I don't know. Let's see. Viscosity is increasing. I don't. Now see, when a liquid is heated, first thing, what can you observe? Whenever you are going to heat something, what is going to increase internally? It's kinetic. The kinetic energy of the molecules is going to increase. If the kinetic energy is going to increase, then the intermolecular attractions are going to decrease. They'll become weaker. Accepted? Now, what do you think should happen to the viscosity? Obviously, it should decrease. the viscosity of the liquid should decrease. Why is it so? Because if you go to the previous slide, what did we say? Viscous force is due to the intermolecular attractions. So when it is going to be due to the intermolecular attractions, when you are going to heat the liquid, the attractions are going to become weaker, due to which the viscosity also decreases. So viscosity is going to decrease with the increase in temperature. Are you able to understand? Second. So what do you say of gases? See, here we are talking about liquids mainly. So what do you think is going to happen in the case of gases? So viscosity of gases is due to the diffusion of molecules, right? It is happening due to the diffusion of molecules from one moving layer to another. But the rate of diffusion of gas is going to be directly proportional to the temperature. Because we'll be studying about it in kinetic theory. There is something called as absolute temperature, which has a relation to the kinetic energy. We'll discuss about it there. So what are they saying? The rate of diffusion of a gas is directly proportional to whom? Directly proportional to the square root of the absolute temperature. Right? Absolute temperature is the one which is measured in Kelvin. It is directly proportional to the square root of the absolute temperature. So what is going to happen to the viscosity of the gas with temperature? So what is going to happen? Viscosity of the gas increases with temperature. But don't worry, in this chapter, we'll be concentrating mainly only on fluids. Right. The next part, variation of viscosity with temperature and pressure. Right. So we saw what is going to happen with respect to temperature. Quick conclusion. So what is going to happen for a fluid, especially a liquid? Sorry. What is going to happen to a liquid? When a liquid is heated, the intermolecular attraction is going to become weaker, due to which the viscosity will also decrease with increase in temperature. Whereas in the case of gases, so what is the reason for the viscosity in the gas? It is because of the diffusion of molecules from when you move from one layer to another. So what is going to happen to the rate of diffusion with the increase in temperature? It is going to increase. How is it going to increase? By being directly proportional to the square root of absolute temperature. So what will happen to the viscosity here? It will increase. Clear with this point? So the next point is supposed to be, you tell me what is it supposed to be? Effect of pressure on viscosity. Let's understand this. First, except water, right? Except water, the viscosity of liquids increases with increase in pressure, right? I'll give you the logic for it. In case of water, what will happen? Viscosity decreases with the increase in pressure for first few hundred atmospheres of pressure. So first thing is, if there is a liquid, okay, when you're going to apply pressure on it, when you're going to increase the pressure, generally what will happen? Will that liquid get compressed or expand? So it is going to get compressed. When it is going to get compressed, what will happen to the relative distance between the layers? The relative distance between the layer decreases, then what will happen to the viscosity? It should increase. That's what is happening here. Makes sense? Next. When you talk about the viscosity of gases, it is independent of pressure because there is no streamlined motion, it is randomly moving. Whereas in this case, you can talk about the streamlined motion. Makes sense? Right. Shall I proceed? See, practical applications and all, I'm leaving it to you. Next, this one. Pause here, okay, so we'll go with the Indian thing. Poiseuille's formula. Let's see what it is. Okay. So first, when we talk about the volume of a liquid flowing out per second, this has a very, very important name. Okay, so when you talk about the volume of the liquid flowing per unit time, you're actually speaking about the rate of flow of that liquid. So what is the amount of volume that is flowing per unit time gives you the parameter called as rate of flow of liquid, which is generally represented by the symbol Q. Okay. So read the statement. The volume of the liquid flowing out per second through a horizontal capillary tube of length L, radius R, under a pressure difference P applied across its ends is given by, okay, there is a formula which we are going to derive. I'll derive and then write it. Okay. See, first, the assumptions used in the derivation of Poiseuille's formula is, listen, the flow of the liquid is steady and parallel to the axis of the tube. So first, let me explain what this capillary tube is. You can imagine a straw. We have a straw, right? We use it for cool drinks and everything. That straw can be considered to be a capillary tube. If the liquid is flowing through it, right? The rate at which the liquid is flowing through that capillary tube of length L, radius R, under a pressure difference. So if suppose I want the liquid to flow with respect to you from left to right, if I want the liquid to flow from left to right, which side the pressure is supposed to be more? Left side or right side? This side, right? So when the pressure is going to be more, it is going to push it, right? So P1 minus P2 is what is the pressure difference P that is given to us, right? It is observed to be proportional to certain values, which we will see. Based on that, we will be able to derive that expression. Okay. So first, even before we start the derivation, right, there are certain important assumptions that we need to keep in mind. What is it? The first thing is, when you talk about the flow of liquid, it is considered to be steady and parallel to the axis of the tube. So if you think of a straw, right, if you think of this, how is the axis of this going to be? Basically, straw is a cylinder. For a cylinder, how is the axis going to be? It will be perpendicular to the area of cross section. So you are saying that the layers of the liquids are moving in the direction parallel to the axis. That is the meaning of this. And it is flowing at a steady rate. Okay. The next is, the pressure is constant over any cross section of the tube. Meaning, if you break it into any cross section, you observe the pressure difference, it is going to be in a proportional value. That is what they have mentioned. Okay. So having said this, the third point is, the liquid velocity is zero at the walls of the tube and increases towards the axis of the tube. So let us say this is the zoomed version of this tube. We saw in the beginning, right? What is the cause of viscosity? What did I say? When I say the cause of viscosity is, as we move away from the fixed surface, the speed of the layers is going to increase. Now read the statement. In the case of the straw, how many fixed surfaces do you have? You have two, the top and the bottom. So they are saying the liquid velocity is zero at the walls of the tube and increases as you move towards the axis. Where is the axis going to be? It is at the center. When this is going to be the midpoint, the maximum speed is supposed to be found at the axis. So that makes sense. You're able to see smaller or bigger. It keeps on going like this. That is what they have mentioned. So these are all the assumptions that are kept in mind. Okay. So there are 5 points actually. The next one is, the tube is held horizontal so that the effect of gravity is zero. Here, when we say pressure difference, right, the pressure difference could have been created because of gravity also. If you take liquid in it, if you're going to keep it like this, what should have happened? The liquid is falling under the influence of gravity. Here, they are saying the effect of gravity is zero. So that is the meaning. The tube is held horizontal so that the gravity does not influence the flow of liquid. So who is influencing the flow of liquid? It is the pressure difference that we have created. It is only, the liquid is only flowing because of the pressure difference that is created, but it is not flowing because of gravity. Right. Okay. Now we'll see the derivation for it on the basis of dimensional analysis first. So the volume Q of the liquid flowing out per second, actually this is volume V. Okay, the volume V of liquid flowing out per second through the capillary tube. What did I say volume flowing per unit time is? It is Q. What is it? It depends on, first, coefficient of viscosity eta of the liquid. Second, it depends on the radius of the tube. And third, it depends on the, see here another term has come. Now you'll understand it better. Pressure gradient. Gradient means what should be the denominator? Distance. And what is the prefix? That should be in the numerator. So pressure gradient set up along the capillary Am I clear with this? Right? Now you tell me, if they are saying that Q is directly proportional to what are all the parameters? It depends on, they use the word, it depends on. So I don't know whether it is going to be directly proportional or inversely proportional, but these parameters will be involved in the expression. Right. So what should I write? I will say the rate at which the liquid is flowing is directly proportional to eta. You know the dimensional analysis, right? What will we do? Eta power A, and it depends on the radius of the tube. So R power B, and it depends on the pressure gradient. So you can write it as P divided by L to the power C. Right. From here, can I write Q is equal to K times eta power A, R power B, and P by L to the power C, where this K is supposed to be a dimensionless constant. So the K is supposed to be a dimensionless constant. Okay. Now tell me one thing. If this equation has to be consistent dimensionally, then what should happen? Both sides should have the same dimension, right? So the dimensional formula of Q should be equal to the dimensional formula of eta raised to the power A, the dimensional formula of R raised to the power B, and the dimensional formula of P by L raised to the power C. Am I clear? Now you tell me what is going to be the dimensional formula of Q. Q is what? Rate of flow of liquid. So amount of volume flowing per unit time. Volume's dimensional formula is meter cube is unit. So it is going to be L cube. So L cube T minus 1. So M is going to have a power of 0. Right. This is equal to, we derived the dimensional formula for a coefficient of viscosity. What was it? ML minus 1, T minus 1. Right. So it is ML minus 1, T minus 1, the whole raised to the power A. What about R? L to the power B. And what about pressure? So pressure is Newton per meter square. So how do you write Newton as? Kilogram meter per second square, right? By, so kilogram meter power minus 1 second square. So what is it going to be? ML minus 1, the whole divided by L raised to the power of C. Is it correct? Check it once. Correct? ML minus 1 T, sorry, T power minus 2. So ML minus 1 T minus 2, the whole divided by L, and the whole value raised to the power C. I hope it's clear. Now collect all M terms. So what will you have? M power A plus B. So it is M power A plus B. Collect all L terms. L power minus A plus B minus 2C. Oh, A plus C, sorry. Yeah. M power A plus C and L power minus A plus B minus 2C. Right. Then T power minus A minus 2C. This is going to be M0 L cube T minus 1. So what will you write? A plus C is equal to 0 and minus A plus B minus 2C is equal to 3 and minus A minus 2C is equal to minus 1. So I know that A is equal to minus C. So when A is equal to minus C, if I take this, or I can say minus A is equal to C. So minus A, I can replace it with C. So here what I can do is minus A, I'll replace it with C. So C minus 2C is going to be minus 1, which implies, how much is it? Minus C is equal to minus 1, or C is equal to, so if C is 1, what is A? So A is going to be minus 1. Since you know these two values, calculate the value of B and tell me. So A is 1, B is 4, B is 4, 4 is correct. You will have R power 4 in the numerator. Previous slide level, idhila pannu. Innum mudiyala first of all. Calculate the value of B and tell me. So what is the value of B? 4. Everyone got it? Yes or no? Got it? Okay. So B is equal to 4. A is minus 1, C is 1, B is minus 4. So I need to take this expression, right? So I need to substitute the values back in this expression. Shall I do that? Tell me, what are we going to get? Q equal to K into eta power minus 1 R power 4 into P by L to the power. So what are we going to get? If you write it properly, you are going to get K P R power 4 by eta L. Right. So experimentally, what happens is this value of K is found to be pi by 8. It is pi by 8. Okay. So Q value will be equal to pi P into R power 4 divided by 8 times eta L. So this is what is called as the Poiseuille's formula, which I told you I'll explain it after derivation. Now I hope you understood. Right. So how did we derive it? Using the dimensional analysis. Clear with this? So first copy the derivation. So write the heading as derivation of Poiseuille's formula on the basis of dimensional analysis. Make it fast. Shall I proceed? Next slide. Go on the next slide. But you finished the next slide. So what was the final expression? Pi P R power 4 divided by 8 times eta L. Done? Rohit? The slide done. Ada? Next, 1 minute. I'll show the next one and then. Secret copy. Last class, I asked you to check one parameter and come. What is it? Blood pressure. Basically, it is 120 millimeter of Hg. Atmospheric pressure கண்டுபிடிக்க தெரியுமா? இதை கன்வெர்ட் பண்ண தெரியுமான்னு கேட்கிறேன். யோசிங்க நம்பர் ஹவுஸ். See 760 வெக்கமா இல்ல சொல்றது. இல்ல 760 mm of Hg is how much? 1 atmospheric pressure. Correct? இப்போ என்னன்னா what I am asking 120 millimeter of Hg will be equal to how much? Unitary method use பண்ண 120 by that's it. So it will be 120 divided by 760. I'm not wanting the exact value and all. Okay. So this slide, what points you wanted to copy these four? Make it fast. Right. So shall we quickly recollect, summarize this topic? So what does this formula speak about? It speaks about the amount, yeah, the amount of liquid flowing out per unit time. That is amount of volume flowing per unit time, right? So it should flow through what kind of a material? It should flow through a capillary tube of length L, radius R, and the pressure difference between the ends is supposed to be P. So what is the expression given as? Given by Q is equal to pi P R power 4 divided by 8 times eta L. So how did we, what are the assumptions that are taken into consideration? First one, the flow of liquid is steady and it is parallel to the axis of the tube. Second, the pressure is constant at any cross-sectional area. Third point, the liquid velocity is zero at the walls. So wherever it is in contact, the liquid velocity is considered to be zero and its velocity will increase as we move towards the axis. And what was the last point? The tube is horizontal so that the effect of gravity on it is going to be zero. It is only flowing because of the pressure difference. So after this, in the dimensional analysis, we understood that the rate at which the liquid is flowing is directly proportional to three parameters. What are they? It is proportional to the coefficient of viscosity of the liquid that is being used. Second, it is proportional to the radius of the tube. And last one, it is directly proportional to the pressure gradient. So that is the value of P by L. And we know that, so you know that in dimensional analysis, for the one which we have, you cannot solve it if you have more than three variables. Right? So that's why here, the third variable is pressure gradient that is being introduced. Okay. So after that, there is a final expression we got. So the derivation process, I hope it is clear to you. Right. So once this is over, the next one is so next concept that is era. So we'll see the next concept is Stokes' law. Okay. So the question is, when we spoke about viscosity, listen to my question carefully. Did we have any solid that was in contact with the liquid? Did we speak about it? So when I told you the layers, right? Did I speak about the layers that are existing between the liquids, or is it between a liquid and a solid? It is between the liquids, right? Whereas there is a possibility not every time we are only concerned about the viscous force. There might be certain scenarios what will happen to understand what will happen when a solid is actually moving through a liquid. Right? And that liquid, if it has viscosity, how is it going to respond to that solid that is trying to move inside? Right. So the topic is viscous drag on an object that is falling through a liquid. So when will Stokes' law come into picture? When do you need to speak about it? When you have a solid that is moving through a viscous liquid. Are you able to understand the difference? Right. So when an object falls through a viscous liquid, the layer of the fluid, right? The layer of the fluid in contact with the object also moves with a certain velocity, etc. So listen, here it is a microscopic level. Let's say this is there is a small pipe like this, in which there is some viscous liquid taken. Okay. Some cylindrical container where you have a solid moving inside. So when you drop a solid, tell me what will be the science involved behind it. Why is the solid even moving in the downward direction? Because of its own weight. So because of the weight, it is going to move the downward direction. If the same solid was dropped from the same height outside the liquid, right? Let's say I'm taking two solids of same mass. So I'm taking two solids. I'm taking them to be at the same level from the horizontal. I'm dropping them at the same time. Which one will have the tendency to travel faster? The one which is outside, because it is not experiencing any resistive force. Right? That resistive force could be in terms of viscous drag or air friction, whatever it is going to be. There is no drag on that object. Whereas what will happen to the object that is moving inside? It is going to experience some force. In which direction will it experience force? It will be in the upward direction. Okay, accepted. It will experience a force in the upward direction, but is that force going to act through the center of mass of that object or tangential to that object? It will act tangential to the object, because read the statement carefully. The layer of the liquid in contact with the object moves with a velocity. So when this object is moving, what will it try to do? The particles that are there with the liquid, right? The liquid particles, will they not try to get stick to the solid? Generally, it becomes wet. When you think of water, right? It becomes wet, right? Why is it happening? How is that wetness coming? It is because the particles are getting attracted. There is an adhesive force that is acting between. Adhesive na period force Fevicol and paper. That is an example. Okay. So the water is going to get stuck. So when it is trying to get stuck, there is an attractive force existing. Will the solid try to pull the liquid along with it? Right. So that is going to happen, due to which that liquid layer will also get some velocity because it is moving. Right. Now that is the case. If you observe the fluid at larger distance from it. So the fluid at larger distance means, let's say this layer and this layer, they are anyways going to be at rest only. But the fluid which is in contact with the solid is going to move. Right. Due to which what will happen is, obviously what is supposed to happen? There is going to be an opposition taking place to the relative motion. Right. So this produces relative motion between the different layers of the fluid itself. So what is the solid doing? It is trying to take this layer along with it, but the layers which are far away are at rest. So is there a relative velocity existing between the different layers? Now you break the layers vertically. So this part alone you have to imagine. I can't explain it. Let's say I give you a bundle of papers. Let's say there are multiple papers kept like this, stacked like this. The paper which is in contact with the solid in the tangential direction will tend to move, but the paper which is far away is going to be at rest. So there is a relative velocity that is existing between this layer and the other one. That is the statement. Right. Now, the retarding force, you can say that the retarding force that is acting on this object is going to increase with velocity. Right. So it is going to increase with the velocity of whom? Velocity of the object. That is, as it is moving down, it is trying to accelerate. Right. Now see. So what does Stokes' law tell us? So this is the science behind viscous drag acting on a solid that is coming in contact with the liquid. I hope that point has got registered. Okay. So I want to tell this point. Listen to this carefully. Listen to this. I want everybody to pay attention. If the liquid is at rest, let's say I take a beaker of water and I put a solid into it, what will happen to that? I'm putting a solid, but it is not going to move. I'm just trying to immerse a solid, but I'm holding it. Okay, what will happen? You can see that the water in the side will get displaced, right? And what will that displaced water try to do to the solid? It will try to push it outside. So there is a force acting at that point. What is the name of that force? That is called as buoyant force or upthrust. Buoyancy is the phenomenon. Buoyant force is also called as upthrust, that is going to act on the object due to the still water. Whereas in this case, what is happening? You took a solid, you dropped it into a viscous liquid. It is experiencing force this time, but this time that force, there will be buoyant force for sure. That is, we'll see about it later. So whenever a solid comes in contact with a liquid, there is buoyant force existing, right? But in this case, apart from buoyant force, what other force is existing? There is a resistive force that is existing. No, I'm talking about the force exerted by the liquid on the solid. So the liquid is the one which is exerting the upthrust. Apart from upthrust, that is apart from buoyant force, what other force is acting on the solid? It is the viscous force. Now, is it not important for us to find out what that value is going to be? Right? See. So according to Stokes' law, like what is going to happen is the backward viscous force acting on a, generally when we say the concept at the top is an object coming in contact with the liquid. They never spoke about what is the shape of it. But when you have to talk about Stokes' law, what kind of a shape are you considering? You're considering a small sphere, right? So the backward viscous force acting on a small spherical body of radius r, which is moving with uniform velocity v throughout the fluid of viscosity eta, is given as F is equal to 6 times pi into eta into rv. How is this derived? Using the dimensional formula. Am I clear? So now we are getting some idea about what is the Stokes' law, right? So did you all write your record? Do you remember writing an experiment for terminal velocity? So in the terminal velocity, you get a value. What is it? 2 by 9 into rho minus sigma. Rho minus sigma though. Say square or other. 2 by 9 into rho minus sigma into r square. R square into g. No, r square into g inverse. And the formula for terminal velocity. How is it derived? Using Stokes' law. Like one of the forces on that object will be Stokes. So here, what are they saying? Now read the statement carefully. What is it? So I want you to be clear with it. Okay. So what is the statement saying? The backward viscous force acting on a small spherical body of radius r moving with a what velocity? Moving with a uniform velocity. Meaning here you can ask me, sir, if it is uniform velocity, then how is force acting? Because force should create an acceleration or deceleration. Here it is moving because it is in dynamic equilibrium. Are you able to understand? So it is moving with a velocity v through a fluid of viscosity eta, and it is given by the expression 6 pi eta r, where r is going to be the radius and v is the speed, and 6 pi is a constant. So shall we look at the derivation of it quickly? Right. So for the derivation of Stokes' law, it was observed that the viscous force F acting on a sphere moving through the fluid is dependent on, first, coefficient of viscosity, second, radius of the spherical body, third, velocity of the object itself. So what should I write? The viscous force that is acting is directly proportional to, you tell me, eta power A, R power B, and B power C. Next step is So f is equal to k times eta power a, r power b, and b power c. Right. Now you tell me, for dimensional consistency, what should I write? Dimensional formula of f should be equal to dimensional formula of eta to the power a, r to the power b, and b to the power c. Right. So what is the dimensional formula of f? mlt minus 2 is equal to eta. It is ml minus 1 t minus 1 to the power a. And what about r? L to the power b. And what about b? lt minus 1 to the power c. Am I clear with that? Now, if you take the values mlt minus 2, this will be equal to what will you get on the right hand side? M power a. Is it not minus a plus b plus c? L power minus a plus b plus c, and t power minus a minus c. Now you equate both sides. A is equal to what? So a is 1 and minus a minus c is minus 2. Right. So minus 1 minus c will be minus 2, which implies c is equal to how much? 1. Then what about minus a plus b plus c? Minus a plus b plus c is also 1. So a is 1 plus b plus c is 1 is equal to 1. This will get cancelled. B is also 1. So what is that you can conclude? In this expression, if you substitute back ABC, you will get f is equal to k times eta power 1, r power 1, and b power 1. And what is the value of k that was found experimentally? It is 6 pi. So from this we can say f is equal to 6 pi into eta into r into. Am I clear with this point? Right. Right. No. So with respect to this topic, what are the 2 points we discussed? One is viscous force acting on an object in contact with a liquid when moving through a liquid. What was it? When an object is moving through a liquid, it will carry some liquid along with it. Then what will happen to the layers which are far away from the point of contact? They are going to be at rest. So due to the change in the velocity, there is going to be some relative velocity that will be created between the different layers. Due to which there will be a viscous force that is going to act on this object. From there, what did Stokes' law speak about? The viscous force acting on a small solid sphere, right, moving inside a liquid with a uniform velocity v is given by the expression 6 pi eta r into v. And how is it derived? By taking the dimensional analysis. So what, for starting with the dimensional analysis, what are we supposed to do? It depends on what parameters? The coefficient of viscosity, the radius of the sphere, and the velocity with which the solid is moving. So taking all these things, we derive, we get the expression as k eta rb, and k is replaced with 6 pi. Right? And this is what is the mathematical expression of Stokes' law. There is one last concept that is left with respect to this viscosity concept, where you have the solid and the liquid coming in contact, that is terminal velocity. So once that is done, we will be discussing about another type of fluid called as ideal fluid. Right? In that we have certain mathematical equations. Like I think everybody has learned this chapter, right? So you have something called as equation of continuity. You have Bernoulli's theorem, right? We'll be looking Bernoulli's principle or Bernoulli's theorem. Yeah. So we'll be looking at it. Are you clear with that? Okay. So any questions? Those are online. Is everyone clear? Arvindam, Rutula,
Yes.
and Eric. Eric, are you there?
Yes.
Yeah.
Yes, sir.
Yeah. So I hope everyone is clear now. Okay, guys, we'll wind up then. I hope you remember that tomorrow there is a test. ரொட்டேஷன் வைக்க நீ எழுதணும் எவ்வளவு வாங்கின பார்த்தேன் அப்புறம் எழுது அவிட்டே கேட்டுக்கோ யா Those are online, we can wind up this and ending this session.